Okay, it's kind of a small picture, but this is a picture of how your house might be wired. We've got a voltage source here. Well, that comes from outside. It's an alternating current. We haven't talked about alternating current yet. It's an alternating voltage, which creates alternating current, so you can run things like AC motors in your refrigerator, in your air conditioner, etc. Okay. So maybe you got a light bulb, and maybe you got a refrigerator, maybe you got some other device, and a bunch of other stuff. Well, each of these ideally sees the entire voltage from your source because they're in parallel. And we know how a box is wired if you have that experience. If you're trying wiring it out, you have the two wires, actually three wires, because you carry a ground wire. And those two wires run from your box up to wherever you want your light bulb. Okay, well, the receptacle, I should have a receptacle around here so I could point to it. But if you know, it has a screw here and a screw here. So you put the wires across that screw. And then you have a couple other screws down here that are connected to these screws by conductors. And you then continue the parallel combination, unless it's at the end of a circuit. Okay, at the end of a branch or something. Of course, you branch these circuits and do all kinds of things, okay? Now, the point I want to make here, though, is your wire has to have a low enough resistance that your change in voltage across the wire is small, okay? Now, I have a little delta V and a little blue resistor here. Okay, I'm not sure that's clear, but that's just a little resistance here, here, and here. A little bit of resistance in this section of wire. Then there's a little more resistance in this section and this section. Okay, and of course the same down here. And there's a little resistance across here, but that's usually, you know, that connection runs through thick enough wires over short enough distances that there's very little resistance. We're mainly interested in these resistances and of course in the common sense of whoever's wiring these things, not to use really thin wires to carry really big currents, okay? And there are codes, an electrical code that takes care of all that. If you follow the code, then you're more than safe. Okay, well, in any case, two things happen because of this resistance. One is, if there's a current, of course, the more devices you have in here, the more current you're going to pull. So you have some current. So you have across each resistance. So you get your currents there, and your current, of course, comes in here. Okay, well, the current in this section is whatever this is. Okay, that's the total current you need to run these devices. Your power is your current times the voltage that you lose. The voltage is your current times your resistance and all that stuff. Okay, the simple Ohm's law stuff. Okay, now we've seen this. If your resistance is too big, you're gonna, well, the bigger your resistance is, the more power you're gonna lose. Okay. And of course, your other conditions. This is the voltage across this square divided by R. Square of the delta V, not the delta of the V square. Okay. The less resistance. Did I write that correctly? Yeah, hang on. Make sure I'm thinking correctly here. Talking about relationships. There's a little notational confusion there, so I'm just going to leave that off. But your power is this IR squared, whatever this resistance is in the wire. That much power heats the wire. Okay. Now, resistance of the wire is resistivity. Okay. Now, the longer the wire, the more resistance. The greater the cross-sectional area, the less resistance. Okay. Just the electric field creates the current density, and the more area you got for the current to flow through, the greater the current. Okay. So resistance is resistivity times just depending whether you use delta L over F or L. Okay. The resistance is bigger if you have a bigger length, less if you have a bigger cross-sectional area. That's why I use a delta L here, but we'll just, that's whatever this length of wire is, times its cross-section, or divided by its cross-sectional area times the resistivity, which is typically, like for copper, I think it's about 1.7 times 10 to the negative 8 ohm meters. Okay. So, what you want is a bigger cross-sectional area to give you a lower resistance, which will give you lower power. You got so many joules per second going into this chunk of wire here. If you get too many joules per second going into it, the wire melts the insulation, and maybe you got insulation between the wire going this way and this way. So between this wire and this wire, there's just insulation. Burn the insulation, you get a short circuit and spark, and you can start a fire. Plus you might damage your fuse box or your breaker box. Okay, so you got this. Okay, well, we have that in every section of wire. So that's one problem. The other problem is you have a delta V here, and that's going to be bigger the greater the resistance is. Delta V is current times resistance, which is of course why this happens. Okay. Again, the bigger your resistance, the more your delta V, the more voltage you lose. If you lose too much voltage, you can damage the motors that run things along the circuits. For two reasons: you want to use big enough wire, and you don't want to use too much length. So you want your circuits to be reasonably short. Don't run a circuit from your circuit box to the other end of your basement, then around the basement, up to the next floor, or over the ceiling, down the wall, around here, and then to your refrigerator. Okay? Because that's too much length, and that adds up. Now it's easy to calculate what the resistance is. You know the resistivity, the length, cross-sectional area. You measure the diameter of the wire, find the cross-sectional area, and so forth. Okay? So that's kind of just a synopsis. You also want to use a material that has a low resistivity. Now, there's a time when aluminum wiring wasn't all that uncommon. Okay, and aluminum wiring can work. Aluminum has a pretty good conductivity. Expansion's a little greater, and for a couple of other reasons, you get a little more heating, a little more expansion, and connections tend to come loose. So we don't use aluminum much. Silver would be great, but it's really expensive. And it's not that much better than copper. So for expense and everything else, the default is pretty much copper. Okay, well, that's just a little bit about house wiring. That's the way it looks. Of course, you branch circuits off of here. You can branch off a bunch of other devices. I'm not drawing that very well, but you get the idea. And of course, then you have a resistance in parallel with this parallel resistance. And yeah, so what you get, especially you got a resistance between here and here and come up there. Okay. But generally, everything's just in parallel. The way I've got this drawn, these are just in parallel with all the rest of them, because they all see ideally the total voltage here. So if you got a resistance here, there's a clear path along conductor all the way back to your source. And if your voltage changes are small enough to be more or less negligible, which is what you want when you wire your house, by using big enough wire and sections that aren't too long. You see, there are all kinds of ways to draw a wire diagram. It all comes down to just a bunch of parallel connections. Okay, you usually don't have a resistance between here and here. And actually, that would be a branch. Anyway, that's the idea. Put all that together with all these concepts that we talked about earlier. And then think about how to do this with transmission lines from your power plant. If your power plant is 500 miles away, you have to have really low resistance in your transmission lines, which means you need pretty big conductors, okay? Because you got a lot of length. You don't want a lot of voltage loss. And incidentally, on power, okay? The more your voltage, or the greater your current, the greater your voltage, the less current you need, okay, to transmit your power. I mean, right there. Big voltage, small current. And it's current times resistance gives you your voltage drop. So you want as low a current as you can and as low a resistance. So you use a whole lot of voltage. That's why you do these 750 kilowatt transmission lines, which create magnetic fields, which may or may not cause some problems in their vicinity. Another issue. Okay. All gets very interesting. Now, you really don't want 750 kilovolts coming into your house. That's why you use transformers. Okay, and transformers are simple. I mean, it's simple to understand transformers. Although the design and the efficient design it's a good engineering challenge. But the idea of transformers is you just have so many loops coming in from your transmission line, and then so many loops of wire within that, and the alternating current creates magnetic fields that create EMF in the smaller number of coils, and that steps the voltage down, but we haven't talked about magnetism yet. So we'll talk about transformers when we talk about magnetism. But your transformers, you probably have 600 volts coming along the power lines to your house, and then you got a transformer that steps that down to 220. Well, and then you got the different phases and all that stuff. We'll talk about that later. And what goes on in your box, okay? Like you have a positive and a negative and a neutral. And if you connect the positive to the neutral, you get 110 volts. If you connect the positive to the negative, you get 220. And that's basically what you have in your house. So not going to get too deep into the practical aspects of it. Of course, electricians are experts at knowing how to connect things and what to connect. They have they don't have the, typically they don't at least have the depth of knowledge of the physics, but they know what works. Physicists, you put a theoretician on one of these things and you're going to blow it up. Okay. If you don't know the practical aspects as well as the theoretical aspects, you don't want to be doing it. Okay. Unless you know the practical aspects really well. That's what technicians concentrate on. And engineers are kind of halfway between technicians and theoreticians. Okay. They got a deeper understanding than the electricians, but they probably don't, you probably don't want them wiring your power plant. Okay. Although there are some people who are both. Okay. So that's just a little perspective on the whole idea of engineering. Okay. Okay, well, in class today, we did an exercise where we had some words written on Post-it notes. The words were, well, among the words, we had a few more than this, but just to demonstrate resistivity, conductivity. Resistivity and conductivity really measure the same thing. If you know one, you know the other, okay? It's just one is reciprocal of the other, and we should know that. We have current density, electric field, cross-sectional area, length, free charge density, potential difference, resistance, current. Now you should hopefully be able to read those. I've got the thing zoomed in pretty well. Let me zoom in just a little more. I'm a little afraid of losing focus, but and let's move over here a little bit. Okay. Now, the exercise was put some of these things together, and the exercise that I specified was put three of them together such that if you know two of the three, you can find the third. Okay? So we need to, in order to do that, we need to understand the meaning of these quantities. Well, one, for example, could be what do I have? Okay, we got current density. So let's put current density up here, along with cross-sectional area. And current. Well, the simple relationship here is the current density times the cross-sectional area. You know, if you don't know what current density is, then you might not know this, okay? So there are three things that can be put together. So let's kind of put those up there. Okay, now, another one that occurs, and we did have on the list, was drift velocity. So I'm going to put drift velocity up here. Okay. Where it's potential difference in the length of the wire go together to give us the electric field. Okay. Now the electric field, along with some other things, determines the drift velocity. The more electric field, the more quickly your charges drift. Okay. Another relationship, and I'm not going to do all the rearrangement of these because that's something I really want to leave to individual students to take these quantities and rearrange them. You can use Post-it notes, and you can draw it on a piece of paper in any way you want to. But there are a number of relationships between these. For example, well, here we have this one. If you know your resistivity or conductivity in the cross-sectional area and the length, you can get the resistance. Okay, if you know drift velocity and the density of conducting particles, conducting charges, and of course the charges in those, but in this case, let's just think in terms of electrons. So you know the drift velocity, the charge density, and the cross-sectional area, you can determine the current. You want to think through stuff like that. Okay, so this whole exercise, I think, was very useful. Then I've got another set of these: forces and power and kinetic energy and energy conservation, basically. And you can do a set of these for any constellation of concepts and understand at a much deeper level than if you're just manipulating symbols in a formula, what's going on, which gives you much better ability to think through and solve problems, identify the relationships, and then conceptualize the relationships so that you can rearrange these in any number of different ways. Then the arithmetic, the mathematics, the algebra or the calculus actually becomes much simpler because it makes more sense and you become a more powerful problem solver. So we spent most of the class time on that sort of an exercise.